Okay, welcome to the last segment of the Fourier sine and cosine series. So, okay, did you realize one thing? Let's look at the intervals. So far I was giving you minus 2, x, 2, minus 1, x, 1. Do you see something that I have been focusing on? These intervals are symmetric, right? With respect to 0, it's from minus 1 to 1, minus 2 to 2. So the question is this now, that's what I want to answer. What happens if the interval is not symmetric with respect to the y-axis? So let me give you an example. I think I will illustrate my point better that way. Let's say this is the function. I'm making this up, okay? And let's say that this is the L. And you see what's going on over here? I have from 0 to L. I don't have the negative. So what can I do? All right? So there are three options that you can do in this particular case if the interval is not symmetric. Okay? We can do 1. I can do even. Okay? How am I going to do even? So then I'll do this. Let me actually copy paste. I'll be right back. Okay, there are two of them, so I draw them to save some time. So I can make it even. In order to make it even, so let's draw it this way. You can see I'm trying to draw symmetric with respect to the y-axis. I'm not sure I was able to accomplish that, but just to also another illustration is this is minus L. Okay, so that's what I have over here. So this is the even. I can make it odd. So this is the second one. It can be odd, which means that it will continue like that, and then it will be like this. Okay, so this is minus L as well. So this is the range that I'm interested in. So this is odd, or this is kind of new now. I can translate it. What that means is I simply do this. See, this is minus L. I have something like this. Okay, you see, it goes to the 0, and then I just translate it, right? So that what this means is, mathematically speaking, this is going to be fx is equal to fx plus L, right? I'm simply going ahead and adding L to this value. This becomes 0. I'm simply adding this L value to here. It becomes this value, etc. Okay, so it's like a repeating. But whatever the method that you choose, we will use the expansion still as if I will be doing from 0 to L like the previous. Okay, this is not going to change the way that I do. I want to highlight that. So let me illustrate this with some numbers. I think that will be better for all of us. Okay, I'm back. So the question is this: find the half-range cosine and sine expansions of this particular function. I selected an easy one because I don't want to, focus on the mathematics component, and I want to highlight how to approach this. That's more important at this point in time. So I have, let's say that this is 1/2, right? And this is 1, so it becomes like this. Okay. Even means, as we discussed before, I will have this then. Let me repeat this. So I simply go ahead and do this, right? This becomes minus 1/2, and this becomes minus 1. And you can see what just happened. So in this particular case, I will follow the same rules that we have established. I will have my a0 present, an present, bn will be equal to 0. So I will find my a0 and an. As I gave you a relatively simple equation, you will see it will be not that too bad of a case. Okay, and this will illustrate how to do the p and all as well. Okay, so p in this particular case is 1, right? Because I go from, look into this. It's the, now it becomes minus 1 to 1, right? So it's p is 1. So then p drops out over here. So p drops out. And f of x, let's look into that. Well, what I will get is 2 by 1. And then I will have 1/2 to 1 dx. So I have 2x, 1/2, right? So if you put 1 over here, it's going to be 2 minus 1, 1. So I will get my a0 to be 1. How about an? It will be a little bit more involved, but still it won't be anything that surprises me. F of x times cosine and pi x by p dx. P is 1, so it becomes 2, 1/2 to 1, because 0 to 1/2 is 0. I'll have f of x is 1, so I'm not going to write this. So it's going to be n pi x by p is 1, so I'm not going to, go for it. And then if I take the integral of it, this will become n2 by n pi sine n pi x, and I need to put this from 1/2 to 1. So it becomes 2 by n pi. So then I will get sine n pi minus sine n pi by 2. Well, I mean, it's obvious we know this is 0, sine n pi, right? We've been doing this for a while. So from here, your an will be minus 2 by n pi times sine n pi by 2. Now let me write the Fourier half-range cosine expansion. So this f of x is going to be a0, which is 1 by 2, plus the summation over n is equal to 1 to infinity, and an will be right up there, 1 then pi sine n pi by 2 times cosine n pi x, because p is equal to 1. And let's do this in parentheses. So this will be my expansion for half-range cosine. Okay. Let me change color so I start fresh. This will be like this to 1/2. This will be -1. Then it will be like this, right? Okay. So do you remember that a0 was 0? So I don't have to worry about it. An is equal to 0. I don't have to worry about it. Bn will be the question mark that I'm trying to assess over here. Let's write it. Bn will be 2 by p integral f of x 0 to p, let's not forget that, sine n pi x by p dx. The process is very similar to the previous, right? So bn will be equal to p is 1. I'm not gonna repeat again. 1/2 to 1. F of x is 1, so it will be sine n pi x dx. P is 1. So I get myself 2 by n pi, I should have a negative sign, negative cosine of n pi x, right? And I have to evaluate this from 1/2, right? So then from here, my bn will be 2 by n pi, and in parentheses, it's going to be minus cosine of n pi, right? That's what I have a negative in front of it. Negative becomes plus cosine of n pi by 2. Okay, so if I have this, then it's going to be 2 by n pi. I will have -1 to the power of n, but there's a negative in front of it, so I'm going to write this. I have done this a few times now, so I'm not going to do one more line just because of that, okay? So that's kind of it for Bn. Then my Fourier series half sine expansion is going to look like this. I have a0 is equal to 0. This is infinity. 2 by n pi, then I have -1 and +1 plus cosine of n pi by 2. This is my bn, and sine n pi x, because p is 1. So, and this whole thing is defined 0 to 1. That will be the range, okay? So this completes the approaches that we have established. The next approaches, I'm going to have the complex Fourier series. I'll be right back, okay? Thank you for watching this segment.